Okay, in this video, we're going to be comparing confidence intervals of of Z's to T's, and we're just going to review the concept of the confidence interval. So first off, the reason we collect data is we usually don't know something about a population and are forced to take a sample in order to use it as a proxy or estimate of the population of the parameter. Let's just say we wanted to know the income of students at Reagan. Well, we probably don't have that information, but we can take a sample to estimate it. But if we only have sample data, we are never able to say what the exact population mean is. So if I only have a small sample, I don't know exactly what people earn at Reagan. However, we can claim with a certain level of confidence that the population mean or population average lies within a specific interval or range. That range is called a confidence interval and is comprised of two components, the estimate and a margin of error. The estimate is the sample average, all right? So the best guess for the population mean is the sample mean. And the margin of error is based on how much spread and how much confidence we have. So when we're working with the Z distribution, we were working with a formula that looked like this. Our sample mean plus or minus the population mean, plus or minus some Z star, and then the population mean divided by the square root of n. So that's what we were working with before, but here we had the population standard deviation. With a T distribution, we're working with the sample standard deviation, but otherwise it's exactly the same. X bar plus or minus, well, instead of a Z star, we have a T star, S divided by the square root of n. Well, our best estimate for the population, is just our X bar. So this is my best estimate. This part right here that I circled in blue is the margin of error. Just like this is the margin of error for a Z. Both of these, the ME stands for margin of error. Now this part right here is known as the standard error, and that would be this part right here. So the formulas are very, very much the same. All right. Okay, so what can we say about our confidence interval? Well, because we only have sample data, we're never ever able to say what the exact population mean is, which is kind of sad because we'd like to know it. But we can estimate and say, oh, it's between this and this. So what we say is we are 95% confident that the true population mean lies within our interval, or if we did a 90%, we are 90% confident. And we can also say that if we do this over and over again, we expect our method to capture the true population mean 95% of the time. All right. Please note, this is the list of things we cannot claim. This we just said. But please note, we are making a claim about the population mean and not the sample mean. We're making a claim about the population mean and not the sample mean. In other words, we don't need to make a claim about the sample mean because the sample mean will lie in the center of the interval 100% of the time. All right. And another couple things that you should note. As we increase the confidence level, the margin of error or spread increases. How about this? As we increase the confidence level, the width of the interval goes up. All right. As we increase alpha, our confidence level decreases. All right. As we increase alpha, our confidence level decreases, and the interval width goes with it as well, because confidence level and width go together. So as we increase alpha, the confidence level goes down and the width goes down. And then as n goes up, the width goes down. And you're like, well, why is that? Well, it's because n is in the denominator and we're dividing. So as n goes up, as the sample size increases, the interval width, as n, the sample size increases, the interval width decreases. Now, we have done a bunch of confidence intervals for z, and I want to compare them to the t because the t has more area in the tails, and we talked about that in our previous video. So we said that the t has more area in the tails. So let's take a look at this. We have a confidence level of 0.68. They're telling me they're centering this on 0. They're also centering this one on 0. And they have a population standard deviation of 5 and a sample of size 4. And we're going to do that all the way down, and we'll just do those real quickly. All right. And of course, we can do that very rapidly by going stats, test, z interval, number 7, z interval, which is what we used before. And our standard deviation we're saying is 5. Our x we're saying we're centered at 0. N is 4. And we're going to do a 0.68. And we get that value. If I do the same thing again, stats test, z interval, and I increase that to 0.95, we get these values. And we'll go ahead and do it one more time to increase it to a 99.7% interval. Because that way we're following the empirical rule. And we end up getting negative 7.419. Well, that was working with the z. Let's contrast that with the t and see what happens. So we're going to go stats, test, and it's very easy. We're going to just go to t interval, which happens to be number 8 on your calculator. And my x bar we're setting at 0. Our standard deviation is the standard deviation of the sample. And it's because of this being a sample standard deviation that we knew I needed to use a t. So this is 5. And we're going to make our confidence level 0.68. And we'll notice we get this value, negative 2.97. And it's a little bit lower than this. And the positive 2.97 is a little bit higher than this, but not substantially different at 68%. Well, watch what happens when we go to 95%. Oops. Stats test number 8, t interval. And I'm just changing the confidence level to 0.95. And when I do that, I get negative 7.956 and 7.956. And now this is at 5 and this is almost at 8. So this is 3 lower and 3 higher. So we've gotten a lot wider. And the reason we've gotten wider is the t distribution has, once again, more area in the tails. Then I can stats test 8 t interval. And we're going to change this to 0.997. And we ended up with negative 22 to positive 22. And wow, this is a whole lot wider here than this one is here. So the t interval, once again, has more area in the tails. Now that was centered up on 0. What if we centered these up on 3? So this is now centered at 3, and this is centered at 3. We're going to keep our standard deviations the same, but we're going to rerun these and just show the shift. That is very easy to do. So stats test, because we have standard deviation of the population, we're going to use a z interval. And our x bar, we said we're centering at 3. Oops. Sorry. Stats test number 7 for z interval. And I have to use a z because of standard deviation of population. X 5, 3, and 4. And my confidence level is 0.68. and we get these values. If I rerun it, doing the same thing, but with a 95, I get this value, these values right here. And then I'm going to rerun it one last time with the 99.7, then we'll make the comparison to the t. So stats test number 7, confidence level of 0.997. And there it is running with the t the 99.7 for the z, and we're using a z because we have the standard deviation of the population. Over here we have standard deviation of the sample, so we have to swap over. So stats test, and now we're going to go to number 8, which is the t interval. And I need to change my standard deviation, put it back in as a 5. Please note we have an x bar at 3, and my confidence level is 0.68. And 0.02 is a little bit below 0.5, and 5.9 is a little bit above. So this is a little wider, but not substantially in the center. But when I get out here to 95% and I'm out farther in the tails, I find that it's substantially different. So stats test t interval, all I'm going to do is change that to 0.95. And we have a negative 4.956 and a 10.956. So this is almost at 2, and this is almost at -2, this is almost at -5. So this is a lot lower. This is almost at 8, and this is almost at 11. So it's a fair amount higher. So this is a whole lot wider than this one. And once again, it's wider because the t distribution has more area in the tails and is a wider and shorter distribution and a little bit fatter. So stats test, doing the same thing for the last one. I'm just changing the level to 0.997. And we end up getting negative 19.23 to 25.23. And we can see that, wow, when we're the farther we get away from the center, the lot more spread out we are. So there's more area in the tails with the t distribution than there is with the normal. Now, once again, as a review, we use the z or the normal if we have the standard deviation of the population. If we have the standard deviation of the sample, we have to use a t. So standard deviation of the population, we're going to use a z or the normal. Standard deviation of the sample, we're going to use a t. All right. And then lastly, the t distribution has more variation or more spread, so there's more area in the tails than for the normal. Consequently, our intervals get wider, and they get a lot wider when we get further out. So the higher our confidence, the wider our interval is going to be. Okay, so this is kind of a diagram showing how those confidence intervals work. And we're going to start with the z distribution, where the standard deviation of the population is known. All right, so we have this, so it's going to be a z because we have the standard deviation of the population. So the population for the confidence intervals in the charts below is highly skewed. So they're telling us the underlying data is skewed. But we have a large sample, a sample of 50. So by central limit theorem, the distribution of the sample means is approximately normal. All right. So consequently, we can go ahead and do this even though the underlying distribution is the population underlying distribution is skewed. Well, if I were to run a 90% confidence interval, it'd be some mean x bar plus or minus z star, and I got z star doing a second var's inverse norm. And I'll just show you where that came from real quickly. Second var's inverse norm, parenthesis 1 minus 0.90 divided by 2. Mean is 0 because it's a z, standard deviation of 1. And please remember, we always use the positive value. So I ended up getting a 1.645. Now, the sample mean comes from the sample standard deviation comes from the sample. So that I don't know because I don't know what each sample is going to give, but I know that this is going to be my Z star and I know this is my sample size. All right. Well, the fact of the matter is, if I know the standard deviation of the population, if the population is known, it's not going to change because I know that value. If I know the standard deviation between the grades is 3.2, then I know that that's going to be 3.2. As a result, this value is constant, this value is constant, and this value is constant. And so the intervals all have exactly the same width because these values are constant. But my sample mean could vary. I could have a sample average of 82, a sample average of 85, and so that's going to move up and down. Well, if this line represents the true population mean, 90% of the time, our interval will capture it. All right. Now, it doesn't mean it's going to be in the center of it. It just means that somewhere in the interval, and these are little interval marks, we're going to capture it 90% of the time. Well, 90% of 20, because there's 20 of them, 90 point would be 18. But that also means if we capture it 90% of the time, we're going to fail to capture it 10% of the time. And 10% times 20 is 2. And look, if I notice here, I missed it. I didn't capture it. And here I didn't capture it. So twice I didn't capture it. So basically the confidence interval says that 90% of the time, and that would be the rest of them, the true population mean lies somewhere in the interval. Sometimes it's barely in the interval. Sometimes it's real close to where the sample average is. All right. But it also means 10% of the time I don't capture it. So in this case, please remember, when we're working with a Z, we knew all these values, so this part's constant, so the only part that's varying is the sample mean. When I get over to running a T distribution, we don't know the standard deviation. And by the way, this is the same scenario, except we're using the standard deviation of the sample. Up here, standard deviation of the population is known, so it didn't change. But every sample is different, so every standard deviation is going to be different. Consequently, some are going to be narrower and some are going to be wider. This value is constant. This value is constant. This one's going to vary. And this is going to vary. So I probably should have labeled these as C for constant, C for constant. Those aren't going to change. But that's going to vary and that's going to vary. But because this can get smaller or wider, I'm going to have some very narrow intervals and then some really wide intervals because some are going to be spread out and some are going to be narrow. Now, once again, this is a 90% confidence interval. And we said that 90% of the time, when we have 20 of these intervals, we'd capture it 18 times if we did that much. And 10% times 20 is 2. And sure enough, we don't capture it here. And this little small interval there didn't capture it. Now, obviously, sometimes it's going to be pretty close to the mean, like it is here. And other times, we're not going to be very close. But basically, 90% of the time, the true population mean will lie in there. We will, once again, notice this is a constant, this is a constant, and this is a constant. The only thing that varies is the sample mean. Over here, the sample mean varies. T star is a constant. This is a constant because it's the sample size that we selected, but this is going to vary. All right. In the next video, we will actually learn how to run one and actually run a confidence interval.